Okay. As Antonio already said, I'm going to talk about neutrino mass and chiral symmetry breaking. This is an idea which we have been developing with my colleague Fedor Simkovich, who visited us several times, I mean, in Valparaiso. So this is, in my opinion, is quite curious idea, which allows relating a small neutrino mass with the small scale of chiral symmetry breaking. Small in comparison with other physical scales, such as electroweak symmetry breaking scale. Yeah, okay. So what is the idea? Okay. We definitely have in quark sector a scale, physical scale, related to the breaking of chiral symmetry, which is of the order of QCD scale around 100 MeVs. Well, but quark sector and these QCD features are not available for a lepton scale, lepton sector, which is QCD blind completely. So then we need some portal to connect these two sectors. Portal which would transfer QCD effects such as chiral symmetry breaking from the quark sector via some portal to a lepton sector, and in such a way to contribute at least or create a non-zero Majorana mass. I will be talking about only Majorana mass, and I will comment why. Well, portals. This what I mean. This would be some interaction not existing in the standard model, and possibly generated by some physics beyond the standard model at some UV scales, ultraviolet scales, larger or much larger, depends on the realization, of larger than the electroweak symmetry breaking scale. So then small QCD scale, chiral symmetry breaking scale, passing through this portal, which is which lies at rather large scale, goes down to the lepton sector, and due to the hierarchy between these two scales, may produce. This is the hope, and I will show how to realize, implement this idea concretely. Result in a small neutrino mass, kind of seesaw. This is a seesaw philosophy, actually. Okay, so then this is an estimate to illustrate this idea. So then by dimensional counting, just by dimensional counting, QCD scale should be scaled out by UV scale, high UV scale to the power 3, and by dimensional counting there should appear also electroweak symmetry breaking scale, because all these operators can appear only, well, but we are interested on the effect of these operators after the electroweak symmetry breaking. This is a kind of very a qualitative explanation or
Why
presentation.
Power 3?
Yeah. please repeat. I didn't hear you. Excuse me, Ivan.
Why is the power 3 and not other?
Well,
powers?
this is I will show. This is just to illustrate
Yes.
because yeah.
Okay.
I will show why. But one can play with this, of course, with these scales and end up with the conclusion that even only by dimensional counting it should be like that. It is just to illustrate the idea in a very general way, so that not to hide the idea in the formalities. So, well, just to introduce, to start, I of course should remind you. You all know that in the standard model, in a pure standard model, without an extra singles like right-handed neutrinos, neutrino is massless. Neutrino is massless, no flavor violation, and so on. In this case, the model is U1 invariant. It features U1 symmetry related accidental. This is an accidental symmetry related to the lepton number conservation. Very well experimentally confirmed, verified this conservation. So then this symmetry is really very, how to say, well established one. But okay, we all before going to the beyond the standard model, there is everybody spelled some words like the standard model is the most successful theory ever created by humanity, but it has some internal drawbacks. One of them is neutrino mass, small neutrino mass, and several others. But no direct experimental evidence of any deviation from the standard model is not yet detected. Well, but we know nevertheless that there must be some beyond the standard model physics at some scale, UV scale, larger or much larger than the electroweak scale. This is the philosophy of the effective theory, so that all these theories should be mapped on the effective operators, some effective operators constructed of the standard model fields, quarks, leptons, Higgses, and must be standard model gauge invariant. And with each operator must be associated some UV scale, and this UV scale should be sufficiently large so that this effect would not be observable as not be, how to say, not contradict to the experimental observations. Well,
but you should put n equal 5 until
from 4 from 5.
Yeah, right.
5, yeah, well, but it was just a copy pasting, sorry. Yeah. But from 5, of course. So then lambda standard model Lagrangian consists of only dimension 4 operators, and then the other operators, irrelevant operators in the terminology of quantum field theory, belong to this part of non-normalizable operators. And then, without specifying BSM physics behind these operators, we are looking for an operator which would connect or offer us a portal, quark-lepton portal between these two sectors according to the idea which I presented before. First of all, yeah. So we are looking for, first of all, we are looking among these operators those which break U1L of lepton number conservation by 2 units in order to be able to generate Majorana neutrino mass, which Majorana neutrino mass is a quantity violating in 2 units this symmetry. Well, it is well it is well known that these operators, lepton number violating operators in 2 units, are the odd dimension operators starting from 5. Now this is n equal to 0 from operators starting from 5. And up to an arbitrary n. The most famous example of this kind of operators is the Weinberg operator, constructed of Higgs and lepton doublets. Higgs lepton doublets, contracted, SU2 contracted, which is standard model gauge invariant with an appropriate scale which corresponds to high ultraviolet physics, which could be a low energy limit in low energy limit could create this operator. And after the electroweak symmetry breaking, it is clear that this operator generates Majorana mass of neutrino of this order of magnitude with some coefficients, numerical coefficients of the order of 1. So this is the in a sense the same scheme when we use a portal between Higgs sector or sector of electroweak symmetry breaking with a neutrino sector, which is insensitive to directly to the electroweak symmetry breaking. It doesn't have any coupling to at the level of renormalizable operators in the standard model. It is not connected to Higgs sector. So then we are looking and found among those operators, non-renormalizable operators, found this Weinberg portal to transmit this electroweak symmetry breaking to the neutrino sector, and in this way to get mass of neutrino. The only it is well known drawback of this in a phenomenological sense of Weinberg operator that it requires very high ultraviolet scale to create, to guarantee that neutrino mass is sufficiently small at the scale of at electron volt scale. So then we need in this context, in the context of this mechanism, UV scale of this huge order of magnitude 10 to 12 GeV. Which entails physics, underlying physics behind this operator. Very heavy physics with the particles, new particles of the order of this scale, very, very heavy particles, which, of course, are far beyond the scope of the current and the future, any future experiment. So then in the literature, there was a lot of efforts to improve this situation. Again, in the phenomenological sense, to make this new physics more behind the neutrino mass, more accessible for the experimental observations. And the models there is a huge number of models of different kinds. In general, there are models which are studying the loop realization of this operator, so that this operator is not realized at tree level, but realized that some loopness, some number of loops, and then from one can gain loop suppression, sufficient loop suppression to make this scale at the TV in the TV range. Yeah.
Why does it have to be odd in this operator in dimensions?
Well, Claudio, this is, let me just to skip this fact. It is a known fact. I can show you why, and maybe can send you reference, appropriate reference. So then operators violating, effective operators violating in 2 units, lepton number have this dimension. Because, well, I have a limited time, and this requires really some. Yeah, okay. I can send you. Just remind me, please. I will send you a reference. Okay. So then.
Yeah, I have one comment, Sergey.
Yeah, sure.
I think that you're saying that the neutrino mass is what you wrote in there is sort of not because you can realize the Wander operator using different ways, using seesaw, and the 3 ways of doing that introduces new particles, and the seesaw is different. So you don't get that neutrino mass like you were saying there.
Ivan, but seesaws
But
are
not exactly like that. I mean,
sure. Excuse me. Okay, please go ahead. Yeah. Can I ask? Can I answer? Well, this is all the seesaws are behind this are some UV completions, 3-level completions of this
Right.
Weinberg operator.
Right, that's what I'm saying. And then you introduce new particles. You have to, and the seesaw depends on those particles too.
But this is this Weinberg operator encodes all the seesaw mechanisms, like this classical mechanism, seesaw mechanisms. Yeah, but this is also known feature or maybe shortage or drawback of seesaws, that the seesaw messenger should be very heavy. And in this case, the mass of the seesaw messengers is translated in the language of effective operators to the scale. Well, but this is just introductory part. Okay. I don't know if I answered your question, Ivan. Maybe I didn't get your point.
Yeah,
but
my thing is only that in order to realize that operator, you have to introduce other particles. I mean, the way you put it, and you get the 3 types of seesaw that way.
Of course.
And
but
then get new particles that produce a different sort of seesaw that you're mentioning there. I mean, the seesaw really could contain those particles. That's what I'm saying.
Well, but
That's okay. Yes,
But yeah, but seesaws, as I said, are ultraviolet completions of this operator. All the seesaws can be mapped to this Weinberg operator with the same result that the seesaw masses of them should be very, very heavy, very large. Well, but this is not the main point of my talk. This is just the introductory part to smoothly introduce the idea. So then, well, loop realization. So then you impose symmetry on this theory, which forbids forbids at tree-level some operator, this one, for instance, and is kind of softly broken and allows loop realization of this operator, and so on. Or we can go further or to higher dimensions of operators, and for instance of this kind, and see that okay, this could solve this issue with the phenomenological irrelevance of the physics beyond the well, behind the small neutrino mass. In this case, well, the suppression could be reached sufficient suppression for large n's, values of n for lambda around the TV. But the question always is why these operators and not this leading operator? I'm going to comment this. This is a key point in all this how to say business. Well, our proposal is the following: to look more carefully at the dimension 7 operator, lepton number evaluating operator, but with these quark bilinears. These are light quarks from the first generation. This is electroweak doublet, quark electroweak doublet, lepton doublet, and Higgs. This is could be both participate involved in this operator, both quark bilinears in a standard model gauge invariant way. So this is an operator allowed by the standard model gauge invariance.
What is Q there?
This is a quark doublet. This is a quark
Okay.
doublet. So yeah, U L D L.
Okay.
Electroweak quark doublet.
So you
And
have
this is
quarks or something? You're
excuse
going
me?
to have quarks?
No. Only first generation quarks.
Oh,
Because
the
yeah.
notation, the notation there is this is not an anti-commutator, right? It's like either
No. No, it's just set. Now I will give a. This is like a set of two bilinears.
Yeah.
Both of them can participate. No, it is not. Oh, yeah, sure. It is very misleading. Excuse me. Sorry. No, it is not anti-commutator. Okay, this is yeah, just the sum of these bilinears with the particular couplings. Yeah, but I return back to the first or the second slide with the idea. So to realize this idea, we need a portal, quark-lepton portal. This is operator. This is the lowest dimension operator, quark-lepton operator. So and this operator, we hope that this operator would allow us to transmit from the quark sector the chiral symmetry breaking effect to the neutrino sector in such a way that to play again, as I showed before, with the hierarchy of these scales, QCD, well, chiral symmetry breaking, it is of the order of QCD scale, a bit different. And this large UV scale at which this operator is generated by some new particles. I am not going to discuss, to refer any ultraviolet completion, any model, ultraviolet model which in the low energy limit at the electroweak scales generates this operator. I'm following the way philosophy of the effective field theory, considering only the effective operators. And this is enough for my purposes. Okay, so then this is the portal, a quark-lepton portal, violating lepton number in 2 units, because we need this violation in 2 units. Quark sector is lepton number neutral, so then cannot produce any lepton number violation in order to generate Majorana neutrino mass, which is the quantity violating in 2 units, lepton number in 2 units. So
and
then this
baryon number, right?
Excuse me?
Baryon number also is violated.
Yeah, this operator portal should violate, and it violates because of this lepton bilinear in 2 units.
The quark part violates baryon number also, right?
Quarks do not violate, do not are not sensitive to lepton number. They violate in this sector, chiral symmetry is violated. And I want this
Talking
effect.
about baryon number.
No, it's not violated.
Excuse me? I don't hear.
I'm talking
Please.
about baryon number, not lepton number.
No baryon. Excuse me. No baryon. I'm not interested in this context of baryon number, of course.
Baryon number, that's what I'm saying.
What violates baryon number? This bilinear?
Because of the Q's that are.
No.
Violation
These are
of baryon number, no.
no. These are neutral. Baryon number 0. Anti-quark quark. So baryon number is conserved by this operator, of course. But among those operators which I showed in general SMEFT, standard model effective field theory, there are, of course, because this is an accidental symmetry, baryon number. This is an accidental, the same as lepton number is an accidental symmetry, which in principle can be broken by some physics beyond the standard model. But you, of course, should be careful with this violation, of course. Okay, so then let me go ahead. So this is in more details the operator in components. No, not in components. In more details. This is absolutely standard model symmetric Lagrangian operator. Yeah, please.
Can you hear me?
Yeah.
Mr. Sergey,
Yes.
sorry, I arrived late to the meeting, but what mean quark-lepton portal? K and L are the shade of the group. I don't know, sorry.
What is the quark-lepton portal?
Yes. What
This
do you
is
mean?
just a nice
K
word.
and L
Nothing.
is the
This
number of the shade, is the shade of a group, the quantum number of a group. Or what do you mean the letter K and L?
Well,
Is quantum number or only is the description of the chair.
Yeah,
chair,
this
sorry.
is a chiral symmetry. Sorry, chiral symmetry. This is the scale lambda, right? This is you mean this one?
Not Q and L portal. Sorry.
Quark-lepton portal.
The letters are the quantum numbers or chair
No,
in a group.
no, it's just quark and lepton. Quark-lepton portal. This is
okay, only the name. Oh, okay,
quark-lepton portal.
okay.
No, it's not B minus L. No. It's, oh, yeah, sure. This is a quark-lepton portal. Well, but I tried to save the space here. Well, okay. Well,
Okay,
looks a bit misleading. Yeah. Okay. Sorry. Yeah. Sure. Okay. So then let me proceed. In components, this operator brings the following terms: left, right, U quarks, DD quarks, and graphically it corresponds to this vertex with the two light quarks and two neutrino legs corresponding to this lepton number violating bilinear. Well, and now we are at the point to benefit from the rich structure of QCD vacuum. We know that due to the strong QCD dynamics, quark pairs, quark-antiquark pairs can form condensate, chiral condensate, which breaks spontaneously chiral symmetry of QCD. This is a global symmetry broken by this effect. Whatever effect is, well, it is just, I mean, origin of breaking is it leads to appearance of gallstones, of course, which are pions. Well, but I will comment about that a bit later. This is just several words about chiral symmetry. So then it is broken by spontaneously by this is a global symmetry broken spontaneously by quark condensate, chiral condensate. And as a result appear triplet Goldstone or triplet of Goldstone bosons, which are pions. So then what does this mean? That the vacuum, because the vacuum is full of this condensate. This is like Higgs condensate. We also have in vacuum an admixture of this condensate. Then we can immerse two quark legs into the vacuum, and instead of these two legs, instead of these two fields, instead of these two bilinears, we would have a number, chiral condensate. This is what we proposed in this paper. And then we can immediately estimate the contribution to neutrino mass. After the electroweak symmetry breaking, this leg should be, this field should be replaced with the Higgs vacuum expectation value, electroweak scale. And this bilinear, quark bilinear with the, should be replaced with the quark condensate, and the scale at which UV scale at which this operator is generated by some BSM beyond the standard model of physics appears here. So that after substituting the the value approximate value known from the light meson phenomenology and from the lattice calculations. This is around of this value approximately, and lambda in the TV ballpark. We would have neutrino mass at EV or even at sub-EV scale. Then in this mechanism, even at the three-level realization of this operator, we have, remember, I commented that in order to improve the phenomenological situation with the Weinberg operator, one could try to realize this operator at loop level to suppress by loop factors and make lambda and new particles which are associated to these two UV completions of this operator. Yeah, but in this case, we don't need this loop suppression. Even at this three-level, we get correct neutrino mass value at the TV scale. This means that the particles in the UV model behind of this operator, particles, scalar particles, or maybe, I don't know, fermionic, no, scalar particles or vectorial particles, which can generate this operator in a low energy limit, could be not heavy and phenomenologically accessible, experimentally accessible. This is one of the advantages of this scenario. Well, everything looks not bad, but as always in real life, in our cake we find a big grain of salt. Because looking simultaneously at this operator, which we found and analyzed it simultaneously with the Weinberg operator, we of course noticed that these operators, at least at first sight, looks much more suppressed than the Weinberg operator. This operator, Weinberg operator, looks dominant, less suppressed than this operator. In general picture, without details, of course, one can design UV completions in which this operator originates from some more heavy particles in propagators, you know, after integrating out some particles more heavy, and while this operator is associated to the particles more light, so then this operator could be more suppressed because of lambda is much, in this case, is much larger than in this case, but this is not fair play. To proceed in a more natural and reliable way, we should find some reason why this operator is more phenomenologically significant than this operator, Weinberg operator. We should find some reasons how to suppress this operator or forbid this operator while not touching this operator which we need. The common way or common wisdom is known. We should look for some symmetry which does this work. The symmetry, a symmetry which would forbid this operator, Weinberg operator, while allowing our quark-lepton operator. This is the way out. At least one of the way outs. I don't see other way outs. This is, in my opinion, the most reliable way out. Let us see what are the most general features of this symmetry which we need. First of all, we want the symmetry to be intact down to the the chiral symmetry breaking, down to low energies, so that this symmetry works even after the electroweak symmetry breaking. Then Higgs should be G singlet. This group with respect to this group. Singlet should not transform under this G group. Yeah. In this case, the electroweak symmetry breaking, when it develops H, develops a wave, would not affect this symmetry. Yeah, looking at this operator, we find another feature of this symmetry, that because HH are singlets, G symmetry singlets, this bilinear, lepton bilinear, must be G non-singlet, any non-singlet representation of this group, without specifying the group. These are the most general features of this group we need. If we want this operator, quark-lepton operator, to be not suppressed, we need compensate this non-singletness of this bilinear. I mean, we should compensate the transformation under G group of this bilinear by the quark bilinears, these two bilinears, so that this product would be, or products would be G singlets, so that this operator would be invariant under this new symmetry, G symmetry. Then, in order to make this job, this symmetry, under this symmetry, H must be singlet, lepton bilinear non-singlet, quark bilinears must be non-singlet, anti-non-singlets of the lepton bilinear, to compensate to make this product, quark-lepton products, singlets invariant under this G group. So this is a G group which I am looking for in order to forbid this operator and let to leave this operator 07. But okay, there are a number of examples which I could offer you, but U1 and so on. But this reasoning leads us to a disturbing conclusion, that Higgs couplings of light quarks, both U and D, are suppressed by, should be suppressed by this symmetry, just because quark bilinears QU are non-singlets, while H are singlets with respect to this group. They are not invariant under this group, G group. Then electroweak symmetry breaking does not generate U and D quark masses. So then the so-called current masses of these quarks are 0. Okay, looks strange and weird, but maybe not so fatal. for the model. Let us see. Well, first of all, we find that if these masses are zero, then pi mesons are massless, which contradicts to the observations. Why is it is so? They are gallstones of a global symmetry. They are massless after, they are massless. To engender them a mass, non-zero mass, we need breaking, explicit breaking of chiral symmetry, soft breaking of chiral symmetry. If these masses are non-zero, they provide this soft breaking and contribute to pion mass. Also, this result contradicts to lattice calculations, QCD lattice calculations, which show that they must be both non-zero. On the other hand, this result looks in line with the fact that these quarks of first generation quarks are special, very special. They are much lighter than the other quarks, much lighter. So that in many models beyond the standard model, these couplings, Higgs couplings, are realized, as I already commented in the context of Weinberg operator. These couplings are realized at loop level. At the loop level, so that to suppress them and make their values very small in comparison with the masses of other quarks. So this loop suppression mechanism also, this mechanism resorts to some symmetry softly broken, which forbids tree-level realization of these couplings, but allows loop realization. I'm not going to consider these examples. We developed several models together with Ivan, Antonio, and colleagues. So then, anyway, we should clarify this situation with this result of masslessness of these quarks. There are basically three or two possible solutions. UV solutions on expense of some ultraviolet physics beyond the standard model physics related to some high energy scales larger than the electroweak scale and so on. This is an example of the operator which can provide soft symmetry breaking of chiral symmetry. Another possibility is solution is infrared solution based on non-perturbative effects of QCD and some combinations. I will show that UV solutions are not compatible with the with the dominance of the dimension 7 operator, which I discussed previously. So then the only solution we are left with is infrared solution. I will show why. Okay, so we need a source for the mass of U and D quarks. This could be an effective operator of this kind. Well, this is chiral operator symmetric with respect to the chiral symmetry, chiral group. Let us see what in components, what it has. So it has these bilinears. After the chiral symmetry breaking, this operator brings immediately U and D mass terms of this form. Well, the question is, what is the scale of this operator? Could be in principle ultraviolet scale, very high scale. Could be. So that masses, quark masses could be very small, because now we know the quark condensate is around 100, a couple of hundreds of MeV. What is the scale? Well, the scale is surprisingly is very, very small. Is in an operator generated at the QCD scale. This operator is really well known in the context of Nambu-Ioannala-Zinio model as a model, as a chiral low energy symmetry, effective theory of QCD. The reasoning is very behind this is very very simple. This diagram generate this operator. Well, this expression with the gluon propagator. Gluon propagator in a truncated theory, which means the case when we send the momenta of all the quarks to zero. This propagator can be reduced to this function depending on the momentum transfer is reducible for a small k squared to this propagator. But this is what I am now saying is how many minutes I have. Antonio?
Yes.
How much I have time?
It's around, yes, and 15 minutes more.
15 minutes. Okay. Yeah, it's okay. 15 minutes is okay. Okay. So thank you. This result, yeah, this result can also been can also be justified in as far as I know in ADS QCD, even with Valery made papers on this subject, and as far as I know, but in that case, this lambda QCD is a bit different, but this scale is a bit different, but at the scale of QCD, of the order of QCD scale. Okay, so then we have this effective operator, point-like effective operator in this truncated theory. After Firtzing, we get this operator with this particular coefficient. With this particular coefficient, I will use this expression for further analysis of this scenario. Well, what is numerically now the value of this mass generated by this operator? Of the order of chiral condensate. This is a well-known mass non-perturbatively generated by QCD constituent quark mass, but it does not solve the problem of P0 mass because it does not explicitly break the chiral symmetry. This mass appeared after the spontaneous symmetry, chiral symmetry breaking. So then we have we should keep looking for other solutions, other sources of U and D quark masses breaking the chiral symmetry explicitly. Okay. Well, first, and there is the only way to way out. I don't motivate why. It's just as a matter of fact by just by explicit verification can be shown that we should reduce our scenario to the operators with only one bilinear in this operator, O7. So, but it is enough. One quark bilinear is enough to realize this this scenario with the chiral symmetry breaking linked to neutrino mass. So I choose this bilinear to participate in this operator, so that G, this coupling of this bilinear, D bilinear to the rest of the fields is 0. Okay. How does it help us? Let us see. So then nothing changes from the viewpoint of the neutrino mass. It does not affect reducing to only one quark bilinear. Well, but in this case, what is an advantage of this case? We do not need to require that this quark bilinear, which does not participate in O7, we do not need to require this bilinear to be G non-singlet. It can be G singlet, so that the Higgs coupling, Yukawa coupling of this bilinear remains allowed by this symmetry and allows non-zero mass of D quark. While U is still 0, is still massless, But okay, at least in this more reduced scenario, we have explicit chiral symmetry breaking by MD. Unfortunately, it is not enough for light meson phenomenology. For light meson phenomenology, we need both D and U quarks be non-zero. Masses, this D and U masses non-zero, those masses which break chiral symmetry explicitly, not those masses which okay, how to go back. Masses, not those masses which generated by the chiral symmetry breaking. No, we need both U and D masses explicitly breaking the chiral symmetry. Okay, and also lattice calculations demonstrate that both these masses should be non-zero. What are the way out? Non-perturbative effects of QCD. The well-known can save this situation can be saved by the so-called 't Hooft instanton vertex. Well, instantons are topological solutions of QCD, which are very well studied from various points of view, theoretical, mathematical, and phenomenological. It is known, this vertex is known. This vertex is known. It involves light quarks, SUD quarks. Okay. How can it help us? In our scenario, MD is non-zero. MS, we are not limited with the strange quark mass. Well, it is non-zero. But then this vertex can generate U quark mass in the following way. We can, having this masses non-zero, MS and MD non-zero, we can close the diagram. These legs, strange quark and down quark legs, so that we obtain mass term of U quark, which is proportional to MD and MS quark masses. So then this mechanism does not work with in our previous scenario with the initial scenario with MD0. We need the MD non-zero. Then U mass can be generated. Actually, this is not our result. Was of course studied long ago, and the most recent updated study was done in this paper, and the result is for U quark is of this value. Mu instanton generated, the Mu is of this magnitude. Okay, so then instantons seems to solve MP 0. I mean, the problem of zero mass of p mesons in this scenario with this result, which should be compared with the lattice result. Very similar, but there is some tension. Of course, there is some tension between these two results, but surprisingly, they are very close, these values. And some additional analysis is needed, of course, from both sides, from the side of the instanton contribution and lattice calculations, to see if this tension is significant or not. So then, in principle, with this, we have a reliable scenario, but there is again, as always, a difficulty. What is the difficulty? At first sight, at least, that this operator, dimension 7 operator, if we have non-zero effective mass, at least effective, of U quark mass, this U quark mass non-zero, then we can close these two legs and get an operator which is very similar to Weinberg operator, because this quark bilinear is equivalent to Higgs. What to do with this? At least we should study with more details this point. This loop diagram can be calculated with this result, where lambda U is a cutoff scale of the loop integration. Cutoff characterizes the scale at which this effective mass, it depends on the scale, this mass. It was generated at the scale of QCD, at the QCD scale. and these non-perturbative effects are disappearing exponentially with the scale. So then this m in fact depends on the scale, and there is a natural cutoff for this integral. This is a cutoff kind of form factor of this mu effective mass. Okay. This effective mass of U quark consists of two parts: constituent quark mass, constituent part, which originates from chiral symmetry breaking, and this instanton generated mass. This mass is much larger than this mass, 200 MeV versus 2 MeV. So then we can neglect and estimate this mass to be, well, we already estimated this mass, constituent quark mass. This mass, both of these masses are generated by non-perturbative QCD. Then the characteristic scale of this mass is at the lambda QCD or so. Now we can combine both contributions, the contribution from this dimension 7 operator without closing this loop, which we previously analyzed, plus this loop contribution. And we see now that this loop contribution is just independently of the details of this calculation is small. Alpha S divided by this large factor. It is just a correction. It's just a correction. But the key point for that this diagram is subleading is that this mass is generated at the QCD scale. It is that this is infrared generated mass, not ultraviolet origin.
Then, Sergey,
Yeah. Yes.
then alpha S should be a scale, very low scale. So why do you think that's small? Seem to be the
Well, but this is should be. It is not. This is also debatable, and in the literature, of course, it is not very small, but there is a saturation. There are various studies, many studies of the infrared regime of this alpha S. I assume that there is a freezing regime, the so-called. And by the way, in the ADS QCD, also, as far as I understand, there exists, is realized this regime freezing in the infrared limit. But okay, this is alpha S at some scale below the GV scale. Entonces, so this is what I wanted to comment. That it also depends on the interpretation of this alpha S. But if this alpha S is in this sense is not very large, in a view of this very large factor, this should be not very large. This is not a proof. This is the reasoning. But in my opinion, is has some this opinion. I mean, this reasoning has some background, but is debatable. This is what we have. But what I want to comment is that if this mass is generated in ultraviolet, then this scale would be some UV cutoff scale, electroweak scale or larger. Then in this case, this correction would be significant, because in this case we have a cancellation of this scale and this scale. If this scale where this mass is generated would be very large, ultraviolet, above electroweak scale, so then we would have a ratio of this electroweak scale and QCD scale squared, very large contribution. Then my conclusion would be, I commented about that, that there is no, at least I don't see any ultraviolet solution of those problems which I mentioned, that in this scenario pion mass is 0. So only infrared solution. When this effective mass is generated at the QCD scale. And this, of course, this question is still open about the size of this coupling. But well, if I if I say these words that okay, there is a freezing regime in IDS, QCD, and so on, this coupling, this alpha S should not be very large. It is like, I don't remember, like around 0.3 or 0.5, something like that. But it is divided by this large factor. So then I hope that this contribution is irrelevant. Yeah. So this is the conclusion about this model. So it looks justified, at least at that level which I discussed. Yeah. And we also studied the last interesting phenomenological feature of this model. Of course, this operator contributes to the neutrinoless double beta decay, and surprisingly, the prediction is very not very is quite restrictive, in the sense that this scenario predicts normal ordering, only normal ordering. Only in this case, this scenario is compatible with the neutrino oscillation data. So then the prediction of this model is normal ordering of neutrino spectrum. And this limits on the neutrino mass eigenstates. With this, I can I finish. I finish with this last comment, because I feel I already exhausted all the time for the seminar. So then, please, questions.
Many thanks, Professor Sergey, for the very nice talk. Questions?
Thank you.
Yes. I have a question.
Continue.
Please.
Please.
It seems to me that you have this effective sort of theory in which you have effective leptoquarks. I mean, if you can put that in terms of effective theory of leptoquarks or something like that. And it seems to me that
In which sense, excuse me, Ivan, where are the leptoquarks? I didn't introduce leptoquarks.
No, I know, but it can be put when you have, for example, even if in the sort of neutrinos double beta decay, you can see that You can convert. It's an effective theory. It looks like an effective theory of vector quarks negated by Higgs somehow. I don't know, but it seems that there is a lot of phenomenology that can be done here. I mean, that you haven't really done. I mean, this is because the scale you are using is not so large.
Not so large.
Then there are a lot of things that can be.
You mean phenomenology of this dimension 7 operator, right? You mean a phenomenology of this dimension 7 operator? Because this is a focus of my talk is this operator. Where is this operator? Yeah, this operator. You mean this operator can have a rich phenomenology, right?
Yeah.
Because lambda is relatively small. Yeah, I agree. But to make this phenomenology, neutrinos double beta decay does not require to open this operator in terms of some particles like leptoquarks and so on. So that we studied directly phenomenology of this operator in neutrinoless double beta decay. But at the accelerator, at the LHC, well, this operator can be, I mean, the models behind of this operator can be studied. What we are doing, we already have, in fact, many openings of this operator, and with some ideas of about observation of these particles, but I don't have time to discuss this. But yes, this is the next step, to open this operator and see what fields, new fields, can stay behind this operator, in the sense model with the new fields which in low energy limit leads to this operator. And leptoquarks could be among those fields, new fields. Ivan, I don't know if I at least partially answered.
The L is a doublet, right? You have the electrons too there. Or
of course. There are
a lot of phenomenology related to
sure,
electrons.
of course. And look, in this charged lepton, the where is it?
Yeah, of the electrons seem to be
Right. But this, look, this dimension 7 operator in the neutrinos double beta decay,
right.
it involves electrons, Higgses and quarks, right? And well, there are some other contributions to meson decays of this operator, right?
Mm-hmm. Right.
Okay.
More questions?
G
Goras,
minus 2, the electron should be. No.
Excuse me, Ivan, I didn't get your question.
Of course, it depends. Yeah, but things is measured very carefully, and even the hydrogen atom levels should depend on this.
You mean depend on this operator? Of course, but yeah, of course, yes. Interactions of in hydrogen, yeah, but I don't remember, but we have seen various implications of this operator, but the only how to say, sizable or significant effect we found in neutrinos double beta decay because of lepton number violation. In the case of hydrogen, it may contribute, but in via loops and so on. But and then
I agree.
Boris, yeah, okay.
Understand. Yeah, I agree.
Goras and Bastian. Goras can start, and then Bastian has questions.
Sergey, could you go back to this slide where you mentioned NJL interaction?
Non-renormalizable.
Yes.
Yeah. Sure. Yeah, this slide, right? This slide, right?
This slide, yes.
Yeah.
Now, this is still relevant, I understand, in your approach, that
Not very relevant. Yeah.
Oh, because I just thought, for example, in the truncated theory, this exchange seems to be suggested that it goes to a constant also by this large volume lattice calculations, which suggest that the running coupling at extremely low energies goes to zero, but combined with the propagator goes to a constant. So, of course, at a bit larger energies, you do have large coupling, but then it goes to zero. So this should work there. But as you say, you then have this problem with the pion mass, as I understand.
Right.
Yeah. Okay.
Yeah. Okay.
Yeah.
So
That's
thank you
just
for
a
this
comment.
comment.
Yes.
Yeah. Thank you for this comment.
Bastian.
Okay, thank you for the presentation, Sergey. Well, first of all, I agree with what Ivan said. To me, at least your main operator, it looks like, especially considering this G symmetry, which relates somehow quarks and leptons, to me, sounds like a kind of grand unified theory or something like is in that context like leptoquarks, but it's just an intuition. I wanted to ask you about the Weinberg operator that can you go to the slide? That is
Sure.
of this the appearance of the.
Yes. Just
it was
let me.
one of the last slides. Like the resurgence, you said something like that.
Resurrection.
Yeah, the resurrection. Yeah. It's a very simple question. It's because
just
said
let
that
me reach this.
the resurrection appears at the one loop level.
No. Yeah. A bit further. Yeah, here.
Yes.
Okay.
Tengo otra pregunta. ¿O terminó, Bastián?
Okay. No. I'm not finishing. No, not yet. No, just well, it was not this exactly this slide, but in some part you put the neutrino mass considering the 3 level and the 1 loop correction with this lambda alpha s. The reason that there is no contribution from the 3 level Weinberg operator is because it's forbidden by some symmetry or what?
Sure. By G symmetry, which I introduced.
By the G symmetry. Okay.
Yeah, it is. But it is not exactly Weinberg operator. Weinberg operator would be, for instance, if this U quark would get a mass from the Yukawa coupling with the Higgs at loop level.
Okay.
Then this would be Weinberg operator at 1 loop. But as I said, this effective mass is not generated neither by Yukawa coupling nor by any ultraviolet physics with the.
By the instantons that you said.
There's infrared source of this mass.
Oh. Thank you for the presentation, Sergey.
Thank you for the questions.
Esta interacción rompe universal. Say it in English. this interaction breaks lepton universality?
In which sense, no, I don't consider, don't study the flavors, but in general, they are, look, they are, how to say,
It's only the
can
electrons, right?
involve all the generations of leptons,
Yeah, but
But
you don't
this
have the
coupling-
muons.
Excuse me? I didn't hear you. I didn't get. Ivan,
What?
please repeat. I didn't get
No,
your point.
in the L, you have a doublet, which is a neutrino and the electron.
Could be also
Have also a
mu,
muon there.
right? Of course, whatever.
Well, then a lot of things that can happen with the muon also. Huh?
Sure, of course, but there is no particular predictions of this model in the flavor physics, because this J is an arbitrary coupling. I mean matrix, an arbitrary. So then, of course, may happen, and one can extract limits from from this from flavor violating processes and so on. But we didn't do this.
But you can have things like the muon going to an electron gamma, which has a
So
a
of
lot
course, but
tracking.
again, as I said, Ivan, this operator is a lepton number violating operator. So then it,
Yeah.
we should study lepton number violating processes to see
Yeah.
an effect of this
Yeah,
operator.
right. No, that's right. Sorry.
More questions? Professor Sergey, the question, and for the Charl-leptons, also the mechanism is the same via the condensate and six-dimensional operators.
No, Antonio, because there is no mass term in this operator for leptons, because look, because of this type of the bilinear, it is Majorana bilinear. It is lepton number violating bilinear. There is no terms in the components of this operator like E bar E by condensate. It
I
does
was
not
thinking in the
generate.
other model, in the model that you show for the
Sure,
left line implementation.
of course, yeah, yes, Antonio, yeah, I agree. This is what I'm, excuse me, thinking about how this chiral symmetry breaking effect could be related to lepton masses. Of course, one should look for other operators which conserve lepton number, and this is the task which we can analyze. So
Yes.
yeah, agree, Antonio.
More question from the audience? Last question. The couplings will be as in the standard model. They will be in that theory will correspond to the alignment limit.
You mean I didn't get
For the
your point?
Higgs to the fermion will be in the alignment direction. Or there could be some deviation from the alignment limit.
Well, you mean in this operator?
No, for example, in the left line formulation.
Well, I don't know. We can discuss. I didn't. Dr. I didn't get this point, but maybe. Maybe if you mean some particular model.
Yes,
Antonio.
maybe there will
Maybe.
be, if there is the Higgs, yes, maybe it will be close to the alignment limit. And for this Weinberg isolation, an extra log contribution to neutrino mass.
Yeah.
Via the log of the at quarks. So it provides it's an isopression mechanism for the neutrino masses. Because there is the low suppression and also the small mass for the at quark will provide the quark suppression.
Yeah.
More questions? If there are no more questions, we send the speaker again. We send Professor Sergey for the very nice talk, for the excellent talk, and we meet at the next seminar.
Okay. Thank you. Thank you very much for the discussion. Yeah. Well, see you.
See you.
Bye.
Thank you very much, Professor Sergey.
Thank you. See you.
Thank you very much.
Thank you. See you.
Yeah.
Bye.